Okay, welcome everyone. This is one of our webinar in this series that we carry on within the project SASIP. It is very nice to see that there are some people that is not from SASIP, which is very good. It's precisely what we want to achieve. So today we have Francesca Vittorioso giving a talk. Francesca, I'm very happy to introduce her. Francesca just joined our group in Bologna at the beginning of January. So she's now part of SASIP. In particular, she's part of the 4th WP in SASIP, which is a working package primarily dedicated to the study of data assimilation and machine learning for the CIs. And Francesca is working shoulder by shoulder with Ali Aidogdu from CMCC for the development of data assimilation for the CIs. But Francesca has a story of working on the use of satellite measurement for numerical weather prediction and for data assimilation in the context of the prediction of pollutant. As a matter of fact, Francesca actually, she graduated here at the University of Bologna in 2015, before then leaving to Meteo France, where she has been, CNRM in particular, where she has been working for 3 years, precisely on the assimilation of satellite data, on the use of satellite data for numerical weather prediction. And then she started her PhD, which she successfully concluded in April 2023, I'm tired today, 2023, on the use of IRS satellite measurement for improving data assimilation of the chemical component. And this is what she will talk about today. So this is this webinar, like it happens sometimes, won't be precisely in the area of CIs. So we will hear about the work that Francesca did during her PhD, but I'm pretty sure that methodologically wise, this will catch the attention of many of us. Okay, please, the stage is yours, Francesca. And I wanted to say to everyone that, of course, at the end, we will ask for questions, but if you also want to just pose questions on the chat, I will be reading them and then okay.
Thank you. Thank you, Alberto, and thank you everyone for being here attending this webinar. As Alberto just said, the presentation is about my PhD topic, which ended successfully last year in April. The work was focused on assessing the contribution of the MTG-IRS radiance assimilation into a chemical transport model for the characterization of atmospheric chemical composition over Europe. The project has been carried out at the CNRM in Toulouse, indeed, and was co-funded by Meteo France and by Thales Alenia Space, which is in charge of building the instrument IRS. So let's start with just some basics. Earth's atmosphere, as you all know, is the gaseous layer surrounding the planet Earth, and it presents very complex and specific characteristics that in subtle balance with each other make life possible on Earth, such as, for example, shielding the surface from harmful radiation coming from space, or allowing the surface to reach the proper temperature for the unfolding of life itself. The atmosphere presents a very stratified structure following the average temperature profile. Here you see the names conventionally given to these layers, but the presentation and the work itself have been mainly focused on these two layers, troposphere and stratosphere, the closest to the Earth's surface. The chemical composition of these layers, such as all the others, varies according to the altitude. So temperature and pressure gradients influence the vertical distribution of each chemical compound, and the sources of emission of the gases and their precursors, together with the atmospheric dynamics in chemical reactions, play a role in each gas vertical, zonal and meridional distribution. The atmosphere mainly consists of nitrogen at 78%, followed by oxygen at 21%, while the remaining 1.9% includes all the other gases known as trace gases. Among them is the ozone, which although in very low quantities, in rather low quantities compared to even all the other trace gases, still play a very, very important role, a fundamental role in the unfolding of life because of the chemical processes it is involved in. Ozone is actually a secondary species. It is never emitted, but it always forms through chemical reactions. And well, the green curve in here shows the average distribution of an ozone profile. And as you can see, maxima in ozone are found in stratosphere. 90% of the ozone, atmospheric ozone is found in stratosphere, where it shields harmful rays, UV rays coming from the sun through processes of photodissociations. On the other hand, a smaller part of ozone, percentage of ozone, 10%, is found in troposphere. This usually comes from stratospheric intrusion, in troposphere of stratospheric ozone, or because of reactions taking place in the lower layers involving primary compound of natural or anthropogenic sources. And this can be, on the other hand, very harmful for life. In order to monitor and predict the evolution of the chemical state of the atmosphere, two main tools can be and are usually exploited. First of all, the mathematical methods on one hand. On the other hand, we have a wide and specific observation network that exists and is constantly being exploited and perfected. And the link between these two worlds is done through data assimilation methods. Moving forward to the objective of this project, the primary objective of the thesis was to assess indeed the contribution of a new instrument, which will be launched on board the Meteosat third generation series named IRS, for the characterization of atmospheric chemical composition over Europe through assimilation of simulated data into the model MOCAGE. The work has been focused on the ozone. Plus, the analysis was carried out as a function of the IRS resolution. Actually, as the official IRS was built, a version with an improved spectral sampling, a doubled spectral resolution, was considered and then studied, and it is called throughout the presentation IRS2. So, starting with the numerical model we exploited for the work, this is MOCAGE. MOCAGE is a three-dimensional chemistry transport model, which has been developed in CNRM since years 2000 and which is operational in this center. In this work, well, MOCAGE provides different geographical and chemical configurations. In this work, we exploited the global configuration, which has a 1 × 1 degrees lat long horizontal resolution, and the regional domain named MAX01, which is centered over Europe and presents a thinner resolution of 0.1. For the vertical resolution, again, we have many options, but in this work, we exploited the 60 vertical hybrid sigma pressure level configurations going from the surface up to 0.1 hectopascal. The observations, well, we have really many options for the observation to be used for the monitoring of atmospheric chemical compositions. On one hand, we have in situ observations, which although very, very precise, can be very spread. Huge gaps exist between weather stations, for example, or they are deeply affected by the weather conditions. And then we have the remote sensing. Data from remote sensing for chemistry mainly come from instruments on board of polar orbiting satellites. So they are strictly connected to the satellite overprint. A new era, actually, in the last few years, started for infrared sounders on board of geostationary platforms. There is already GEARS, which is on board of a Chinese satellite, which is focused on Asia. This is why Europe started developing IRS. IRS is indeed an infrared sounder which will be launched on board the METOP third generation sounder series this year, hopefully, and close to Sentinel-4. And it will acquire an entire Earth disk, which will be divided in 4 local area coverages. The most interesting of which for us will be the LAC4, the most frequently acquired, and centered, of course, over the Northern Hemisphere. Well, the main innovation of IRS, even more than the temporal frequency of acquisition, is its spectral resolution. Sorry, excuse me. Well, as you can see here on the on the infrared spectrum, here is the spectrum, but this is just to highlight the 2 bands that IRS will provide, one in the LWIR and another one in the MWIR. As you can see, with a resolution, with a spectral sampling of 0.6 centimeters minus 1, that for an instrument placed on board of a geostationary platform is quite thin, for a total amount of 1,960 channels. As you can see, this will be sensitive, the instrument will be sensitive to many chemical species. So even if mainly designed for numerical weather prediction, for weather monitoring, it will provide a huge potential also for chemistry. So this is IRS. On the other hand, IRS2, this ideal version with an increased resolution, will provide exactly the same bands, but with a doubled spectral sampling. So for a total amount of 3,633 channels. For the way the IRS2 has been thought, which I want to specify, this is not being built. This was just a version to be studied throughout this work. Well, IRS2 was conceived to have a noise which was almost doubled compared to the one of IRS. So this has to be kept in mind for the interpretation of the results. Well, since both IRS and IRS2 are not operational, we had to simulate synthetic observations. To do so, we used the observing system simulation experiments. Well, to build the reality, the nature run and the run of control, we used Mocage, so the same model for both versions. This can be quite tricky because nature run and control run must reproduce the differences that we would find looking at the reality and a model run. So we had to be careful to differentiate them. The meteorological forcing is the same for both and comes from the operational arpège, which is an NWP model operational in Meteo France. So we started using different emissions, modulating the emissions provided to the model, while the nature run was using the emissions in the version operational at the time the work started. For the control run, we used emissions of another year, of year 2000. On the other hand, we also used another slightly unconventional approach. We assimilated into the Globe 11 real data coming from the interferometer IASI on board of METOP. Again, we assimilated radiances. So this study was quite interesting because it led us to study the background errors, some channel selection. This is why we are putting it under the form of a scientific paper, but this is still in preparation. After that, the smaller domain, the regional domain, was taken for the production of the synthetic observations through an observation simulator that in our case was Artetov version 12. Then the instrument noise was added, and the synthetic observations thus found for IRS and IRS2 were assimilated into the control run. The period of study is of 3 months, summer months in 2019. So the first thing to do when producing an OSI is to verify that the control run and the nature run are different enough, but at the same time consistent in order to avoid the so-called identical twin problem. To do so, it was very important to carry out many tests, and this is what we've done. But here I'm showing just a few results, starting with the troposphere, with a comparison in a tropospheric column. Here you can see an average of the ozone field obtained through the from the nature run and averaged over the 3 months period of study. On this panel, we have the same for the control run. Here is the relative difference and the standard deviation of the differences. As you can see, control run values are always lower compared to the nature run, but the spatial distribution is consistent, so this is a good sign. Then, looking at the differences, we see up to 20% of spread of difference on the southern east quarter, probably due to the forcing or to the emissions at the surface. On the other hand, the structure of temporal variability, because this is a standard deviation computed over the 3 months, is geographically localized, as you can see. Another kind of comparison can be done looking at the, instead of a column, of an averaged column, over each layer provided by the model, each of the 60 layers provided by the model. So here we have an average through the longitudes. And again, this is a relative difference, and here is a standard deviation of the difference. Maxima of relative difference can be seen, recognized between 175 and 27 hectopascal, so close to the tropopause, and up to, we can see a difference that goes up to 35%. Standard deviation of the differences, on the other hand, have a maximum around this level, that is the model vertical level 20. Zooming in and adapting the color bar to appreciate the differences in the lower layers, we can see that the lowermost troposphere has a finer structure. Maxima go up to 25% around 36 degrees north, and minima are at the top of the domain. And as you can see, we recognize a stronger variability at the center of the domain. So we can conclude that we are satisfied with the nature run that we obtained, and we move forward in producing the observations. synthetic observation. So both versions of IRS, as already said, will cover similar spectral bands, but simulation and assimilations of complete bands will be extremely time consuming and redundant. And at this stage, we decided not to perform a channel selection. Plus, we are interested in ozone absorption band. This is why we decided to simulate an entire band centered over the ozone absorption area. That is the one here highlighted for both IRS. We simulated a total amount of 195 channels for IRS and 365 channels for IRS2 throughout the 3 months period. Here I'm showing 2 simulated spectra bounded by plus and minus the standard deviations for 1 day, just to have an idea, to have a look at the simulated spectra. And you can recognize the difference in the most frequently absorption rays in the IRS2. So the observations have been simulated in clear sky only, taking the information about clouds from the meteorological forcing, and a thinning has been performed. Well, a thinning, in this case, I mean that we took only 1 pixel per box of 0.4 degrees. Here I'm showing the simulated observation, so in radiances, for only 1 channel, that is this one, the 550, to provide you with an idea of where the observations are located. You can recognize here the disk that IRS will cover, and this is very important for the assimilation step. On the other hand, the holes are due to the clouds. So once we have this synthetic observation, we move to the assimilation. First of all, we'll see the assimilation of only IRS radiances. We'll leave IRS2 for later. The methodology of assimilation exploited is the 3-dimensional variational method, consisting in minimizing the cost function that you see here. Well, as for all the data assimilation methods, a very important step is providing the proper weight to each term, background and observation through the matrices, covariance matrices of the errors. Starting with the matrix of the background errors, we built it. We used the method providing literature, even if the literature for the radiance assimilation into a chemistry transform model is not wide. This is a new field of study. So we took the 2% of the ozone concentration at each atmospheric layer, and then on the other hand, the correlation terms have been modeled using a diffusion operator. For the R matrix, we used the well-known de Rosier diagnostic using innovations O-B and O-A to build a full R matrix, so taking into account also the interchannel correlations. While the observation operator was the radiative transfer for TOF, the RT-TOF model version 12 in clear sky conditions. So we performed this assimilation. This was a sanity check, one of the many sanity checks that we made to verify that the assimilation was well performed. Here we have an hourly statistics over the domain of O-P and O-A. And the standard deviations of the same quantities for 1 channel to resume the behavior actually found for throughout this band. As you can see, there is a bias reduction through the assimilation. Actually, with the assimilation, you see the cyan curve has a wider amplitude compared to the blue one, and with the assimilation, we reduce the value. On the other hand, standard deviation reduces through assimilation too. So we can move on to verify the contribution, to assess the contribution of the assimilation of IRS. Again, on the tropospheric column, we visualize only the results for the tropospheric column. Nature run and assimilation run are, as you can see here from the relative difference, are very close to each other, where the observations are simulated. You can see here the disk I mentioned before. The relative difference goes from 0 up to 3% over the Mediterranean basin, which is quite an improvement if we consider that for the control run, we went from 10 to 20%. On the other side, we have the standard deviation, and we see that actually the minima are found again over the Mediterranean Sea. So we can conclude that assimilation of IRS radiances has a positive impact compared to no assimilation in this case. Again, we can have a look to a cross-section averaged over the longitudes. Assimilation run is again stronger than nature run of 5 to 10% between model 1130 and 20. And maxima in standard deviations can be seen here, you see, but around 28 degrees, from 28 to 32 degrees of latitudes. However, zooming in again in the lowermost troposphere, we can again recognize finer structures, but I want to invite you to pay attention to this area. If you remember, the area where the assimilation was performed was limited, and is this one bounded by these squares. So even if the maxima are found at the border of the domain, they are not actually interesting for the analysis we are computing. And we can, focusing only on this area, we can say that we go up to 15% of variation. And for control run versus nature run, we had a vertical variation up to 25%. So we see again an improvement when the assimilation of IRS radiances is performed. As I just mentioned, many tests have been performed. I showed just the results for the tropospheric column, but when looking at the total columns, we go from a variation of 13% up to almost 0%. So for the tropospheric columns, we can say we go almost from 20 to 3%. And even looking at the vertical levels, as you can see, the improvement is quite significant. Then we can conclude that the assimilation of IRS radiances into mocage has always a positive impact compared to no assimilation. The results just shown have been summarized and put in a scientific paper that is at present submitted at the Atmospheric Measurement Techniques journal. Now we can move to the comparison of IRS2 versus IRS impact. So since the results are very similar to each other, to appreciate the differences, we have to have a look only to the differences. So here I'm showing the difference between the deviation of the assimilation run of IRS2 compared to the nature run and the assimilation run of IRS compared to the nature run. Just to be clear, green values means that IRS2 is the closest to the nature run, to the reality. Red values mean that is IRS to be the closest to the reality. Here we have an evaluation of the standard deviations. Again, blue values mean that IRS2 has a smaller error compared to IRS, to the assimilation of IRS. So, well, I already commented everything because as you can see, we have mainly green and blue. It means that the assimilation run of IRS2 radiances produces values closer to nature run than the assimilation of IRS. We can again have also a look to the vertical structure, looking at the cross-section of the differences between IRS and IRS2. The larger values are found at the southern border of the domain, but they are due to a coupling effect. I didn't mention this before. You probably recognized it on the other charts. Actually, this effect is due to the coupling between the global domain and the regional one. This is why these results can be taken as the truth. They should be either excluded from the evaluation or just taken into account when interpreting the results. And this is what we do here. At the center of the domain, there is a predominance of area where the assimilation run of IRS2 is the closest to the nature run, and the error is smaller. In the lowermost troposphere, again, the best performance is the one coming from IRS2 compared to IRS. So we can conclude that in general, even if the differences are very small, when comparing two versions of IRS, the second of which presents a spectral resolution, which is almost doubled compared to the first one, IRS2, even if the error, the instrument noise is almost doubled, IRS2 still provides a better result compared to the assimilation of IRS, but the values are very small. So to conclude, I'm showing here again the tables I have already shown. I'm not commenting them again because I've just finished to say the same, but I want to leave you with some perspective. This work presents really many perspectives, but among them, first of all, I would like, well, it's not me who will do this, but the comparison of the assimilation of IRS with the assimilation of YASI, which is on board of the METOP, so on a polar orbiting satellite. YASI has been used over the last decades a lot for the monitoring of the atmospheric chemistry, so it would be very interesting. Then IRS, it is official that will provide only principal components. So it will not provide, only principal components will be distributed. So a short study on the assimilation of reconstructed radiances should be done. And why not maybe a channel selection instead of simulating a whole band, performing a channel selection over the spectrum. Plus, another very interesting thing will be the evaluation of the impact of a synergy with other instruments like Sentinel-4, which would be on board the same platform, YASI-NG, or surface data. And of course, the work should be spread over the other areas of the spectrum sensitive to other chemical species. And this is all.
Thank you, Francesca, for this interesting presentation.
Yeah.
Thank you. I'm ready to answer.
Thank you very much, Francesca. It was very nice. I was listening with a lot of attention. So let me first ask to the audience, there is any question? Someone want to break the ice or even in the chat? If you want to make a question, just switch on your camera and your microphone and go ahead. Is anyone? I see Ali.
Am I allowed?
Yeah, Ali, please go ahead.
Yeah, thank you, Francesca. It was very interesting. I was wondering, you already mentioned that the way you have created your nature run is quite unconventional.
Yeah.
But there was a clear bias between your nature run and the control run, which also appears in your statistics when you correct with the assimilation, the control run. Is there a reason why you have chosen that methodology to create your nature run? Because when you do the identical twin, it is expected that they are equally likely your nature run and the control run.
Yes.
Supposed to be. Thank
Yeah,
you.
so I want to specify many things about this topic. I went very fast on it, but it was a huge part of the project. It took almost 1 year of study. This is why we put it under the form of a paper. Well, first of all, my nature run and my control run are the regional domains, so are the Mach 01 in both cases. The assimilation was performed in the Globe 11. So formally, I do not perform assimilation in the real nature one that I use, but this is, let's say, forced at the boundaries by the global domain. Plus, well, as you said, this is, as I said mostly, this is a conventional because you do not assimilate real observation into a nature run. This is why we've done it in the global domain. The choice was done because, well, changing only we wanted to use the same model for both control run and nature run, and changing only the emissions would have affected only the distribution of chemical components in a 3-month period, only in the lower layers. So in a long term, we will not see a huge impact only changing the emissions. So we needed to have some other information, and we decided to do this using SASIP radiances. Plus, what you say, the spread between nature run and control run, is something, I say it's consistent because it's something that we see in reality when using mocage for the, well, in the operational. When we run mocage, we see often an underestimation in certain cases. So it remains consistent with what we find in reality when looking at the real data versus the data that the model provides us, at least in troposphere.
Okay, basically you're not assimilating in the nature run, but you are perturbing the boundary conditions.
Exactly, yeah.
Oh, okay.
You said it better, yes.
Yeah, thank you very much.
You're welcome.
I saw Tiziano, he showed up before, was correct? If so, Tiziano, please go ahead, and then Steve.
Yes, it was. Oh, sorry. Let me.
Okay.
Okay,
Yeah,
okay. Sorry, Tiziano Maestri from University of Bologna. Congratulations, Francesca, and thank you for your presentation. I connected late, and so maybe you told about this, but how many degrees of freedom do you have in the spectrum about ozone, for ozone retrieval? And I almost also curious to know which are the constraints on your radio transfer code for performing the assimilation. I mean, in terms of speed and computational time, are there any constraints?
Well, there are no huge constraints. The only constraint was, well, Artetov is very efficient. It depends on the machine you make it turn on, but it was quite efficient. The problem was mostly the assimilation more than the creation of the synthetic observations. For the ozone, you mean how many, for the degrees of freedom, you mean where we simulated the observations, I think? How many observations we created? I don't know if I understood properly your question. We simulate observations in, well, sorry, are you, okay. I don't think I understood properly your question about the degrees of freedom.
Because in the IASI spectrum, usually when you do a retrieval of the ozone column, you only have 1 point something degrees of freedom. They basically allow you to derive the total column only of the ozone.
Yeah. Well, consider that we have only the information of radiance. So this is the L1, it's not a product. And we assimilate these radiance. So we have the spectrum. Actually, the spectrum, we do not move to the L2. And we assimilate it into the model that has that provides a 3D field. So we have over the entire domain 60 levels. Then it's us computing the total column or the tropospheric column, or taking into account each single layer.
Yes, what I wanted to point out is that in the radiance, you don't have information about any levels. So the information that you got from the radiance is basically a total column or a little more than this from IASI.
Yeah, well, it's going to be almost the same.
I don't know IRS very well, so.
Well, it's going to be almost the same of IASI. Yeah. It's a radiance, so it's exactly as you say.
Okay, thank you.
You're welcome.
Ivo?
Yeah. Francesca, did you have a chance to look at the correction to the different channels compared to the background error covariance? Are some channels corrected better than others, or is it quite proportional to their error variance?
Well, I don't have here, I don't have this on this presentation. Well, the channels are, we had a look to all the weighting functions of each channel for sure, and we took into account plus then only the ozone sensitive channels, also some channels sensitive to the surface, so in the atmospheric window. So for sure in this case we have a better response of the ozone channels, but in general the behavior is almost the same. Is almost the same in the ozone band. Yeah.
Thank you.
Anyone else? Oh, yeah. Hey, Marcello.
Yes, thank you for your very interesting presentation. And when you talk about the thinning of the data, I was simply asking how did you determine the optimal resolution of your thinning?
Trying, it was empirical. Okay. It means that, the model has a 0.1 resolution, consider that. So we, but it was really too much reproducing data for every single box, so 0.1 per 0.1. So we tried, but then we had to also to consider that IRS2 would have provided twice the information of IRS. So really using and reproducing all the data would have been not impossible to reproduce them, but to assimilate them would have had a really high computational cost. So we tried a couple of options, 0.2, and then we landed to 0.4 that looked as a good compromise.
Okay, thank you.
Alberto.
Hello, thank you again for this presentation. Probably I missed something because I have some local technical defiances during your presentation, but my question is, when do you assimilate ozone? I guess that I don't know Mokash, but I guess that it's able to simulate also other chemical species in the meantime, is, let's say, simulating also ozone. Yeah. And let's say the curiosity is on the impact that the simulating ozone could have also in the, let's say, simulation of the other species, if any, relevant.
Yes, I actually performed, and it's not shown here, sensitivity studies taking into account other species and mostly the CO. I wanted to show the spectrum. As you can see here, there is a nice sensitivity to CO and to O, but CO is probably the most interesting to be studied. There is overlapped a thin sensitivity also to ozone here, overlapped to DCO. And this presents for sure a huge potential. And this is why in the perspectives, we put also the simulation, the performing the same study on other species, and first of all, DCO. I had some student during the last year of PhD during my last year of PhD that I supervised, who already started studying DCO, and the results were very promising. When I left, I think there was already the idea to start some thesis working on that. I don't know about the joint simulation, so simulating both together. I did not try, so I don't want to say too much about something that I don't know. But yeah, I hope I answered to your question.
Yes, thank you. Work in progress, we could say.
Yes, let's say that.
Okay, this has been very, very, very nice, especially, a lot of questions, which is, this is good because this gives us the motivate us to go for further webinar, which goes beyond CIs. I hope that Pierre is not unhappy with that. If there are no other questions, then I would like to thank you again, Francesca. It has been very nice, and I like very much also the work very much. I also would like to thank Solène, as usual, for her work on making SASIP going forward. To all of you, we will have the next webinar in March. I think it will be the 19th of March, but stay tuned. I think that Solène will, at due time, she will share the information. We will jump on a completely different topic that will be more on the mathematics of the data simulation. So you see, we try to embrace relatively broad areas. Okay, thanks again. And,
thank you. Thank you very much.
Thank you.
Bye.
Thank you. Bye.
Thank you.